On page 193, the 1 and 2 tail tests information that they've got there is saying, thinking back to the two examples that we've focused on in class so far, that one about Dan the macho man and Leonora and her throwing the die and the number 1 coming up a lot of times. It's in both of those cases, they've made a claim in a specific direction. Okay? Dan has said he's macho, so he's going to have more boys. So the direction is towards boys. And Leonora has said the dice is biased towards the number 1. So they've both got a direction there. Okay? Those are what we consider one-tail tests. So when we're talking about our distribution, whatever it may be, you're only looking at one side of a distribution based upon their claim. Okay? The other side of things is something called a two-tail test. That is where it's ambiguous as to which side you're looking at. They've just said, the die is biased, for instance. Rather than the die is biased towards 1, but the die in general is biased. Actually, that would probably be multiple because there's multiple outcomes which could suggest that. I suppose you could check biased against 1 compared to biased to 1. A better example would be maybe like a coin, okay? A coin can be biased towards one side or the other. I could say the coin is biased towards heads. That's a one-tailed test. Or I could say the coin is biased full stop, and that would be a two-tailed test, which you would have to test either side of that, whether it be the tails or the heads. Okay? So, one-tailed test, you're only looking at one side of a distribution, whether it be the left side or the right side. But on a two-tailed test, you need to consider either side of the distribution. Okay? So, what we're going to be looking at today is how that would work. So on page 194, there's an example that they've gone over. And it's talking about some television programmer of a political show. It's saying that their show is completely unbiased. Okay? It neither favours the government nor is against the government. Okay? Or favours one party more than another. That would be another way it could be biased. So it's saying that if you asked anyone on the street who the show is aimed at, they would say neither way. Well, you'd have a 50-50 chance of them saying they hate the government, or a 50-50 chance of them saying they love the government. That's their claim. So this is setting up a two-tailed test, because at the end it says does this... however, the 10 people selected at random asked the question, does the programme support the government or the opposition? 9 say it supports the government. The question at the end is, does this constitute evidence at the 5% significance level that the producer's claim is inaccurate? Okay, so it's not asking, does that show favour the government based upon the data they've got? It's just saying, is it accurate? Okay, is it accurate to say that they don't favour either way? Okay, so this is a two-tailed test. So, their claim is that it's a 50-50 chance, so we're going to take them on their claim and use that for the probability. Okay, so when you look at the distribution that they show you in the proper bar chart way, but I'm going to just draw it as a curve. And again, this is bad. This is bad maths, me doing here, drawing binomial as a curve. It should be bars. It's just I'm not drawing 11 bars out right now. If we look at that distribution, it's based upon that 50-50 chance. They set up the null hypothesis, being the probability is equal to 0.5, as he suggested. As the producer suggested. Does it actually say the gender? No, it doesn't. Right? Okay, so as they suggest, the alternative hypothesis is that the probability does not equal 0.5. Okay, so rather than it being a less than or greater than, as we've seen before, we've got a not equal to. As soon as you see not equal to, that's a two-tailed test. It's saying it could be either side of this value. Okay, as long as it doesn't equal this value. Okay, the significance level they've suggested is 5%. And we've got this distribution. So they've calculated the probability that no one said that it supports for government probability 1 person, 2 people, 3 people, 4 people, 5 people. That's what that distribution is displaying. Okay. Because we've got a two-tailed test, we need to consider both sides of this situation. Okay. 9 out of 10 people said that they selected at random, blah, blah, blah. 9 say it supports for government, okay? So if this is supporting government, we've got 9 people, okay? When we take our distribution, do we just look at the 9 people? Who else do we need to look at? Sorry?
Everyone under, so 0 to 9.
Not everyone under?
Everyone
above. Yeah, we need to look at 9 and 10, okay? Because it's that side of that distribution. However, because this is a two-tailed test, you also need to consider the left-hand side, okay? So the left-hand side in this case would be 0 and 1, okay? I think it's only possible on this one because it is a 50-50 situation with binomial, okay? It gets a bit more complicated when the distribution is skewed. So have you all seen it before, the fact that a 50-50 binomial distribution displays like normal? Okay, so it's symmetrical. Okay, if it's skewed, it's a bit different, and I'll talk about a skewed example in a second because I actually don't like the example from the book. I think it's kind of potentially misleading in a way. So basically, they've said because it's symmetrical, you're looking at both sides, it's going to be symmetrical on both sides, so I need to consider the symmetrical version of 9 and 10, which is 0 and 1. Okay. They then calculated the probability that x equals 0, the probability that x equals 1, 9, and 10. Okay. And they've just used binomial for this, binomial expansion. So the NCR, p to power r times q to power n minus r. And probability it's 0 is 1 over 1024, 1 is 10 over 1024, 9 is 10 over 1024, and 10 is 1 over 1024. Okay, so those 4 values. To find the overall probability of that happening, they just add it together. So the probability that I'm not going to write that in proper terms actually. So the overall probability is equal to 22 over 1024, which is equal to 2.15% to 3 significant figures. Okay, at 5% significance level, is that significant? Yes. So because 2.15% is below that 5% arbitrary number that they've given us for this situation, we can reject null hypothesis. Okay. And at that point, you'd also write a statement what that means. So this means the probability of someone was the actual situation. They've not actually stated their sentence after they've written the p is not equal to 0.5, but this means the probability of someone saying the show is unbiased, or saying the show supports government or not is not equal to 0.5. Okay, that's my best interpretation of their setup of a null hypothesis there. Yeah?
So why do you have to add them all together?
Because it's the overall probability. So basically, the probability of a right-hand side of a distribution would be 11 over 1024. But because we're doing testing if it's accurate or not, that means we're looking at both sides of a distribution. Because in theory, you'd expect it to be exactly 5. okay? But we're having to look both sides because we're just saying, are they accurate with this? So does that probability not equal 0.5? So we have to look at both sides. So we have to add both sides of a probability together to get that, okay? The reason why I think this is a bit misleading, as I mentioned with reference to skew earlier, is if your thing is skewed, okay, and it was 9 out of 10 or 9 out of 20 or whatever number it is, you can't have the same symmetrical side distribution on the other side. You can't look at that 0-1 case because actually what you consider is not the value itself but the area of probability, okay? So at a 5% significance level, oh, sorry, I wanted a different colour there. So at a 5% significance level, what you should actually be testing is 2.5% on either side. And that's not necessarily going to have the same number of values in both cases. So what I want to actually do as a class, rather than making you go off and do this yourself and finding it out by just having to be told it when I walk around the room, is if we just all have a look at question 4, this is an example where there is skew. So question 1, 2, and 3, I think all of them are 50-50 situations. Okay, question 1's about a coin being tossed. Question 2 is about male-female of birds. Question 3 is about turning left or right. Those are all 50-50 situations which would produce a normal distribution, okay? A symmetrical distribution. Sorry, I shouldn't say normal. It's a symmetrical distribution which looks like a normal distribution technically. Question 4, though, is about a multiple choice question, A, B, C, D, E, and students guessing randomly on each question. So what's the probability of getting it right on that question? 20%, or a fifth, or 0.2. So it's not going to produce a normal distribution because it's only when the probability is exactly a half that it produces that symmetrical curve. As soon as you start changing it, it will move to one side or the other. Okay, so a 0.2 distribution is going to look more like what I've drawn here, with it favouring the left-hand side of the distribution. If it was 0.9, it would favour the right-hand side, based upon above or below the 0.5 probability. It goes to either direction, so below it goes to the left, above it goes to the right, in terms of an image. So what we're actually being asked to do here is set up a test at a 10% significance level, is it? Yeah, 10% significance level to find out if the students' marks were completely random, okay? If they actually did randomly guess. What you actually have to do here is take that 10% significance level and split it in half across the distribution. So we're looking at 5% on the top end and 5% on the bottom end, okay? And it wants you to basically just find what values would suggest that actually it wasn't random, okay? So we need to find that critical value. Remember that from last lesson, the critical value? So we need to find the critical value at 5% significance level on the lower end and the 5% significance value on the upper end. So, because it's, 20 students in the question? 15 questions. 0 to 15 questions. So we're going to find out how many questions can they answer right on the bottom end. What's the lowest number of questions they can answer right and it not be considered significant, and the highest number of questions they answer correct and it not be considered, and it be considered significant enough for you to ignore everything below it, to ignore their statement that they guessed randomly, sorry. So, what was the probability that they get no questions right is the first part that you need to do. So what's the probability that x is equal to 0? So that's going to be your 15 choosing 0 times 1/5 to power 0, because that's the probability we get right, times 4/5 to power 15. I don't know what that is off the top of my head, and I don't actually have a calculator, so if someone could just... is it a good calculator? Am I going to be annoyed by this calculator?
It's good.
Yeah, it's good.
It's good.
What was that, sorry?
3.5%.
3.5. Okay, so, or 0.035. I'll just write down that value. Okay, so that is below our 5% significance level. Okay, so theoretically 0 falls within it currently, but I can't just stop there and go, 0 is my answer. I now need to consider 1. Okay, would adding the probability of getting 1 right to that 0.035 still be below 5%? Okay, so is 1 going to be within that region as well? So I'm going to do the probability that x is less than or equal to 1, which is the 0.035 I've already got, plus the probability of 1. Okay, so it's a cumulative process. Okay, that's why it's quite good to know how to use your calculator and keep the values on your calculator. So for instance, once I get to times 0.8 to power 15, once I've got that value here, I'm just going to add on my next value. I'm not going to keep rewriting it, okay? So I'm just going to add on 15c1 times 1/5 to power 1 times 4/5 to power 14. What does that value give me? 16.7% or 0.167. So that is no longer in my region. Okay, so 0 is in my region, but 1 is not. Okay, so I know on the bottom end of my question, x is equal to 0 is one of the values that would make me go, yes, they weren't guessing randomly. Okay, so if someone in the class got 0 right, they were not guessing randomly. Theoretically. Okay, moving up from that though, I now need to find the upper end of that 5%. But because it's distributed to the left, I'm not now going to go to the right hand side and start at 20 and work my way down, because it's going to be closer to the left hand side of my values, so it's going to be below 7 theoretically. If it was perfectly distributed, 7 would be exactly in the middle. I don't think that's where 7 is going to end up, but 7 would be exactly in the middle, so I'm not going to go 15 down to 7, I'm going to start on the lower end. So that's not a good example of a line. So 7. So I'm just going to carry on from where I am and do what to get the other side of things? I could compare it to 95%. That is one way of doing it. Or I could do what else? 1 minus. Okay. So either I'm going to carry on doing this at 1 minus, or I could compare it to 95%. Both are actually valid here. Okay. It both make sense. Actually, I think the 95% one is almost easier in a sense, but I'm going to keep it to that 1 minus, because that way I'm actually comparing it to 5% and not 95%. But technically it's the same. You'll get the exact same answer. Okay. So all I'm going to now start doing is 1 minus these values. Obviously, 1 minus probability x is less than or equal to 1 is not below 5%, because it's 16%. You know, that's 84%. So I'm going to do 1 minus probability x is less than or equal to 2. So I'm going to take the 0.167 I've already got, add on the probability of 2, and I need to do 1 minus that, sorry. 1 minus this probability times 1/5 to the squared times 4/5, 13. Okay. What has anyone got what that is? 0.6 exactly. 0.602. Okay, so it's not below the 5%. I would then move on to 1 minus probability x is less than or equal to 3. And I would continue this on until I get to that value, which would be below 5%. Okay? I know the answer from the back of a book, but you can work that second side out yourself. I've given you that starting point. So if you want to just carry on that question, see if you can get the x crit value on the right hand side, whatever this value here may be. Okay. Oh, sorry, not whatever value's there, whatever value here. Okay. Maybe. Sorry, this is thanks.
No,
Like, but when we carry on, we can't
no,
add
but that doesn't
0.6,
allow.
02, and then 15 choose.
You're right, yeah. So
Yeah.
maybe it is better to do the 95%. I'm overcomplicating it, I think. Maybe if you just keep doing this value itself and then in your head doing 1 minus, that would make sense. Does that make sense? So rather than doing the 1 minus every time,
Yeah.
in your head doing the 1 minus,
Okay.
would that be below 5%?
Yeah.
Yeah. So if you hit like 96%, you can go, yeah, that's below 5% if I did 1 minus in that situation. In the same way, what is it? Yeah, says. Alright, cool.